Hello, I'm ready. Do you see that?
Yeah, fantastic. We see your slides.
Okay.
So please allow me to say a few words about about your talk. So this this talk will be by Collin Broholm he will be talking about magnetism in some topological magnetic semi-metals. So over to you, Collins. You have 40 minutes. So at the end of 35 minutes, I'll probably give you an indication that your time is running short.
Okay.
You may start.
All right. Thank you very much, and thank you so much for the opportunity to join the meeting. I apologize that I'm remote, and I'm going to be careful because I know that, so I'll try to keep on time. And I'm going to talk about our recent work on magnetism in some topological magnetic semi-metals. So this, I think, is the first talk today that that discusses materials that actually can conduct charge, but maybe there'll be more talks on that a little later today. Here is the outline or the general kind of idea that I'm aiming to consider in this talk. So the idea is that in Dirac materials that have protected band crossing, can be an interesting interplay between magnetic order and charge transport. And you're quite probably familiar with the fact that magnetic order can lift the degeneracy of Dirac points. The result of this is actually the formation of anomalous quantum transport properties that result from the Berry curvature of the Weyl points that form from the Dirac point under the magnetic order. So this I will talk to some extent about this effect, but my interest is actually more in the converse effect, where we explore the impact of the Weyl or Dirac points on the magnetic interactions, on the magnetic order, and on the magnetic excitations in these kinds of materials. And we're interested in whether there are new sort of qualitative features that we could experience in these kinds of materials that have anomalous band structures, but as in terms of the impact on the magnetism. And I've assembled three recent projects that we've been working on that represent various manifestations of these ideas. And I'm in the talk going to progress from I think a situation in neodymium aluminum silicon, where we have fairly well-defined 4f electrons, local moments, whose interactions are mediated by Weyl fermions. And so this happens to be a compound where we know from the structure of the material, it is a structure that breaks inversion symmetry. And so we know that even in the paramagnetic state, we actually have Weyl points in this material. And they were interested in the kind of magnetism that results from that when we have really well-defined 4f electrons experiencing these Weyl fermions. The next topic will be manganese-3 tin. Some of you might be familiar with this material. It has an anomalous Hall effect. And we're going to talk about the magnetic structure that's associated with that. And so I'll present to you our determination of the magnetic order in this material, as well as a fairly new result where we found a quite interesting incommensurate phase that involves a mixture actually of both spin and charge modulation. It's a really complicated state, and I can't say that we fully understand it, but I feel that it could be related to this manifestation of the interplay between the relativistic band structure and the 3D electrons in this case. And then finally, I'm going to go to the kind of most extreme case, perhaps we could say, which is going to be where we have 4f electrons, but they are actually forming some form of a local quantum critical state in a stoichiometric compound. And we think that this may be related to the underlying topological character of the electronic band structure, though it's probably fairly speculative. However, we do have evidence, I think, for local quantum criticality in this material. So those will be the three parts of the talk. So first, about the neodymium aluminum silicon compound. And so I've shown you a picture of the structure. It's a centered tetragonal structure. And it actually, as I mentioned, does not have inversion symmetry in it. And as a result of that, one can show that it actually has a number of Weyl points, 56 of them, in fact. And I'll show you band structure calculations that are able to determine the location of these Weyl points. Of course, we're doing experimental physics, which means that we need an actual compound, hopefully with this crystal structure. And one of the things that can be quite challenging in these kinds of materials is to know whether they actually do lack inversion symmetry. In this case, if there is intermixing of aluminum and silicon, then you can actually reform in an averaged sense the inversion point. And so we need to check that, which we did using neutron scattering, which can actually fairly well distinguish aluminum and silicon. And this image shows you structural refinement that proves it to be in this particular space group that doesn't have inversion symmetry. There's also in the inset a second harmonic generation, which provides direct evidence of the lack of inversion symmetry in the structure. But let's turn to the character of the 4f electrons in the system. This is neodymium, and the specific heat is shown here. And if you look at the inset, that's a plot of the entropy versus temperature. And we see that it ends up saturating around 100 Kelvin at R log 10. It indicates that we have a J equals to 9.5 multiplet. And we would expect generally that this would be broken into 5 doublets, and there would be one of those doublets which would be lowest, and that would be some kind of effective well, it would be a doublet degree of freedom. And what we see in the specific heat is that most of those doublets actually give rise to a broad peak in the specific heat between 10 and 50 Kelvin, but then there are actually sharper peaks occurring around 7 Kelvin and 3 or 4 Kelvin at low temperatures that indicate actual magnetic phase transitions. And we'll be looking at the character of the magnetic order that develops at these phase transitions. Let me show you a little more bulk data or thermodynamic data here. The susceptibility is quite highly anisotropic. It's an easy axis system. The moments are predominantly along the c-axis. And you can see that as we go through the maximum in the specific heat, depopulating the 4 excited doublets, then that's when we end up having a very enhanced Ising-like susceptibility with a big susceptibility along the c-axis. And the lower right corner here, we're showing the resistivity as a function of temperature. And you can see fairly mild anomalies at the phase transitions. And that indicates the kind of the back impact of the magnetic order on the underlying electronic band structure. So that we do see that there is this kind of interplay that's taking place. Let us now turn to the nature of the magnetic order in this compound. I'm showing you some results of neutron diffraction experiments, just kind of the compiled results of measuring the temperature dependence of Bragg peaks. And if you look at the lower left corner, you see the temperature dependence of the wave vector of the magnetic order. And actually, the wave vector is of the two-third O type with a slight incommensurability in the tetragonal basal plane. And with blue, we show the intensity and the position of the first harmonic incommensurate magnetic peak. And then with red, we show the third harmonic peak as well. And so the principal order parameters is the intensity of the two-third O type peak. But then you have coming on upon cooling the appearance of this third order harmonic. and that indicates a squaring up of the underlying incommensurate magnetic order. And this, as often happens in rare earth systems, can only go on that low in temperature, and then you have to go into some kind of a, typically have to go into some kind of a commensurate state, and in this case that actually becomes a ferrimagnetic state, and so that's when this the delta incommensurability parameter goes all the way down to 0, and that actually leads to this third harmonic. Actually then becomes an allowed magnetic Bragg peak, and that corresponds to the ferrimagnetic ordering. And the corresponding structure is shown here, and I think the sketch is actually the commensurate low temperature structure, which roughly speaking, if you take a line of spins that goes along the base diagonal of the tetragonal structure, then it has an up spin in red and then 2 down spins in blue. However, down spins are rocking a little bit back and forth, and in that way, even the commensurate structure, in fact, becomes a chiral structure that has a handedness associated with it. So both the incommensurate state as well as this commensurate low temperature state are actually states that have a certain chirality associated with them. And now let's turn to the question of how this impacts the electronic band structure. And for that, in collaboration with Faisal Tafti, then there is, who also grew the samples, by the way, here's a plot of the measurement of the resistivity as a function of magnetic field, where you can see strong Subhro to Haas oscillations, and they actually give us some insight into the character of the electronic band structure. And you can see that as we go from the as a function of applied magnetic field from this up down down structure to a fully magnetized state, then there's a significant change in the electronic band structure. But even actually as a function of magnetic field within the up down down structure, then there are actually changes in the characteristic frequencies, indicating that there are changes in the underlying Fermi surface. To look into that with some greater care, we subtracted a magnetoresistive background and then extracted the Subhro to Haas oscillations as a function of as a function of field, but also at various different temperatures. And by Fourier transforming those data, we then get the oscillation frequencies as a function of magnetic field, which is shown in these two sketches. And then from those, as you know that the oscillation frequency is related to the extremal cross-sectional area of the pocket that's involved in the oscillation. And from that, we can then extract a linear dimension of the orbit, if you will, a diameter of the orbit. And that diameter we have shown as a function of temperature with the green and the yellow points in this graph down here. And those are being compared in blue with the wave vector of the underlying incommensurate magnetic order, which is also temperature dependent. And what I'd like to point out here is that the rate of the temperature dependence of different experimental measures of the linear dimension of the Fermi surface, they actually are similar rates versus temperature, and that indicates to us that the incommensurability observed is actually driven by the nesting of these pockets formed by the electronic band structure. So this is what I call an experimental indication. But let's now look at the DFT calculation of these effects, and of course it's a fairly short talk, so I probably can't go through it in as much care as I should. But here's the electronic band structure calculated by David Vanderbilt and his collaborators, and from it they were able to extract the Weyl points that's associated with the paramagnetic phase. And then, considering the chemical potential, one can then look at the structures that are formed around these Weyl points, so the Fermi surface that's formed around these Weyl points, and one finds that this two-third wave vector that we see experimentally actually matches the spacing between some of these Weyl points. There are a lot of them, so it's not a specific association that we can form, but there is this matching of the incommensurate wave vector with this dimension of the Fermi surface. And actually, we were fairly careful with this because, as you're aware, it can be difficult to determine the chemical potential or the Fermi energy accurately in DFT for a given material. The material can have a slight shift, and in fact, we determined that shift by comparing to the Subhro-de Haas oscillations, and we obtained the dashed blue line as the indication of where the Fermi energy actually lies. And then with these black points, we show the corresponding with that with those values for the Fermi energy. We show the nesting vectors which extend from a maximum value to a minimum value, and in fact, right at the determined chemical potential, then there's a very good agreement in the length of that nest vector and the observed incremental magnetic wave vector. So we think that there's theoretical evidence that the magnetic order that we observe is actually mediated by Weyl-fermions, because that's the character of the quasi-particles that are associated with those parts of the Fermi surface. So in conclusion, this is a non-centrosymmetric structure which has Weyl-fermions, and we have observed experimentally that the temperature dependence of the wave vector observed in magnetic ordering and in Subhro-de Haas oscillation, that they actually match, and also theoretically, there's a coincidence of the magnetic wave vector with the nesting wave vector. So we think that this incommensurate structure can be said to be mediated by Weyl-fermions. Okay, good. So that was the example of a well-defined rare earth moment living in a electronic band structure that is known to have Weyl points, and then understanding that the interactions are mediated by the exchange of these Weyl-fermions. Now we're going to go to a transition metal material, manganese 3X. Actually, we're going to both look at germanium and tin. In this case, we have a material that is somewhat deeper into the itinerant limit, if you will, and we'll see various indications of this fact. So these are materials that have gained a lot of attention, particularly since a paper in 2015 by Bhattacharjee company, where they found that there's an anomalous Hall effect in this material that can be controlled by the application of an in-plane magnetic field. And this notably occurs in the absence of significant uniform magnetization. Though there is hysteretic in-plane magnetization, so there is some small spontaneous moment that you can deduce from this, but it's on the scale of milli-μb per formula unit. So really, really small component magnetization is consistently present, and is, in a sense, the reason that one is able to manipulate the magnetic order by the application of a magnetic field. So all of this takes place at room temperature in a compound of earth-abundant fairly earth-abundant elements that are not particularly poisonous. So it has a real possibility of an application that would involve the Kagame lattice. So this is, we heard in Philip Mendel's talk about an insulating Kagame lattice material. In this case, it is a metallic material, which means that the interactions are much longer range, and therefore it actually does not end up being driven, if you will, by the kind of frustration that was mentioned in Philip's talk, because they're fairly strong interlayer interactions. It's a really fully three-dimensional, antiferromagnetic material, and it's really important for us to really to keep that in mind. On the other hand, the structure of the Kagame lattice is very important as well, because it leads to topologically protected Dirac points in the paramagnetic state, which then actually end up splitting apart into Weyl points that lie fairly close to the chemical potential. So that's the underlying explanation for this anomalous Hall effect, is that under the development of the magnetic order, then these Dirac band crossings actually split apart, and we get Weyl points that carry Berry curvature, which in turn gives rise to anomalous Hall response and also anomalous Nernst effects. So let's look at the underlying magnetic order in this compound, and I'll start off by looking at the manganese 3 germanium material, and that material seems to be that material has, let me say, this material has a magnetic phase transition just above room temperature, 370 K approximately. And you can see here the specific heat, which looks a lot like a second order phase transition to us. And that's important because that allows us to use representation theory to analyze the character of the underlying antiferromagnetic order. There's a fairly interesting critical exponent that we extract by measuring the temperature dependence of the Bragg peaks. And we don't actually understand quite which universality class this is associated with. There are various other stacked triangular lattice systems that have similar critical exponents, but I don't think there's a really good understanding of where this exponent actually comes from. But having a second order transition, now we can actually use representation theory, as I mentioned, and it turns out that the only magnetic state which involves an in-plane ferromagnetic moment is the one that I've shown here, which is the gamma 9 IREP. And very interestingly, this is a so-called anti-chiral state that involves spins at 120 degrees to each other on each triangle. But there are actually two components to this structure, to this irreducible representation. It can both support a coplanar antiferromagnetic state, as indicated here, as well as a ferromagnetic component. So actually, the basis vectors support both of those things. And so you could say that this antiferromagnetic order must come along with a little bit of ferromagnetism. Energetically, it doesn't seem to be particularly favorable. So it's a very small component, but it cannot be fully extinguished because it has the same symmetry to it. So it's a Q equals to 0 antiferromagnetism, and it furthermore transforms as a ferromagnet. And so in a sense, that's why it has this impact on the Dirac points of splitting them apart into Weyl points, because it really is behaving, if you will, like a ferromagnet, but it doesn't have the magnetic dipole moment. So it's a very interesting kind of stealth ferromagnet, you could almost say. And so we've been doing, full refinement of this structure. It's fairly difficult, in fact, to extract information from about these structures from neutron diffraction, but with a high field and polarized beam, you can actually do it. We've also been looking at the magnetic excitations, and they look like spin waves at sufficiently low energies, and you can see some examples of that in these data. But then when you come to higher energies, then there's a very strong broadening of the spectra, which indicates some kind of decay mechanism. Maybe it's an electron hole pair decay mechanism that eventually damps the spin waves and completely, as indicated. And I think I'm not going to spend too much time on this, but we presented with this kind of situation. We collaborated with Oleg Chernyshov and his graduate student Sayek Dasgupta at the time, and they developed a very elegant method to actually extract information about interactions based entirely on the low energy regime of the low energy spin wave light regime. So you don't have access really to the short wavelength spin waves because they're so damped. But you do have access to things like the gap and the excitation spectrum and the velocity at long wavelength limit, and that's actually enough to get fairly good information about the relevant terms in a phenomenological spin Hamiltonian. This is here it's written down with the relevant terms, and I've indicated the relevant interactions. And I just want to point out that the main interactions turn out to be the in-plane antiferromagnetic interaction within the Kagami lattice and the interplane ferromagnetic interaction between between different layers. And I think I'm just going to skip a couple of slides forward because I think I'll otherwise run out of time to show you the parameters that we eventually were able to extract using this phenomenological long wavelength theoretical approach. So 34 millivolt antiferromagnetic in-plane interaction and the interplane J4 interaction, which is actually ferromagnetic. So again, a fully like three-dimensional order, and this particular set of parameters accounts for the low energy spin waves and stabilizes the magnetic order that we actually observe. So that's the commensurate anti-chiral magnetic order that's observed in the manganese germanium case. And I just want to mention that there's a completely different state that actually develops at low temperatures in manganese tin. And so this is a really complicated magnetic structure that we've been worrying about it for quite a while. So it's but let me see if I can summarize what's going on here. So essentially, just in a snapshot, then in the commensurate state, you have this anti-chiral state on every Kagame layer, and those are actually oriented in the same way. If you will, the ferromagnetic moment is oriented in the same direction. But in this incommensurate state, then actually the ferromagnetic moment and the entire anti-chiral state actually begins to rotate as you come along the c-axis. And we see that in the magnetic diffraction, both of synchrotron X-rays as well as polarized neutrons. And shown here on the left is actually, in the bottom left frame here is shown the two different wave vectors and their temperature dependence. We call them K beta and K chi because the K beta component, as we determined with polarized neutrons, is associated with an out-of-plane magnetic modulation, so oriented along the c-axis. And then we have a in-plane incommensurability, whose wave vector we denote by K chi. Both wave vectors are oriented along the c-axis, but the corresponding spin is modulated in perpendicular directions. So that's the magnetic component we determined by magnetic X-ray diffraction and polarized neutron diffraction. But there's also a charge component that we observe using X-ray diffraction, which is at twice the wave vector, both twice the chi wave vector and twice the beta wave vector. And also there's an interference term between the two wave vectors. So two distinct wave vectors appear, and they start off being incommensurate, and then eventually at sufficiently low temperatures, they end up becoming just commensurate multiples of the c-axis. So I have a little picture of the structure that we have refined using a magnetic neutron diffraction. It's shown here. It's a little bit of a complicated story because the spins are both rotating within the plane and then also coming out of the plane. And then there's the charge modulation that comes along with that as well. Now, the interesting thing that I should mention is that the Hall response, the anomalous Hall response, actually completely goes away when you enter this very complicated spin charge modulated state, and that's shown here actually in an experiment from the Los Alamos group, where the anomalous Hall response in zero field cooled is present in the Q equals to 0 state, but then you transition to the incommensurate state and you lose this response entirely as you go into this incommensurate state. So I'm going to skip this, and I just want to summarize that we have a antiferromagnetic state that kind of has the character of a ferromagnet, and therefore it leads to Weyl points that then lead to an anomalous Hall effect. And then I was pointing out a instability that exists in particular for the manganese tin case into this complex structure that involves an interplay between spin and charge, and where you lose, in fact, the Hall response. Good. So then let me now turn finally to the case of serum ruthenium for tin 6. So this is a very interesting compound, which actually, even though it's a stoichiometric compound, forms some kind of a quantum critical state. I want to show you both some thermodynamic data and then some neutron scattering data that analyze the character of this state and lead us to say that this is a local quantum critical state. So shown here on the left is the center tetragonal structure again, and this also is a structure that doesn't have inversion symmetry. It has a fairly complicated band structure that is, I think it's not fully resolved, but it may have some topologically protected Weyl points in it, but this is not quite clear. And then also shown is here the resistivity, showing this kind of increase towards low temperatures, but saturating at some finite value. Could be because of a surface transport effect. There's no phase transition in this compound, despite serum being having a single F electron, so being a Kramers doublet, but no phase transition, in fact. And then we have the susceptibility has a power law dependence at low temperatures. And actually, if you look at the Grüneisen parameter as a function of temperature, as well as the differential susceptibility, you can extract Silke Passion and company extracted critical exponents. So a susceptibility critical exponent of 0.5 and 0.78 for different field directions. So those numbers become important when we look at the neutron data. The curious thing is that having these power law type behaviors, it indicates that there's a criticality in the system. And normally you'd think of criticality as being in a magnetic system as being maybe indicating a proximity to some kind of an ordered magnetic state. But when you look at the magnetic inelastic scattering, you find only very, very broad features in momentum space, and no indication of impending magnetic ordering at some critical wave vector. In fact, the magnetic correlations are really at the atomic scale only. And we can actually understand the wave vector dependence of the magnetic inelastic scattering in terms of simply a Linhart susceptibility with a phenomenological band structure. We can actually reproduce many of the features that are seen experimentally. And so it seems that a nesting kind of incomplete nesting conditions can actually give rise to these kinds of momentum dependencies. But yes, no indication of a long-range ordering. However, you do see that all of the magnetic response is gapless and is really building up towards energy equals to 0. And you can actually fit the energy and momentum dependence with this kind of susceptibility form, which involves a critical exponent alpha. And by analyzing all of these data, we obtain a value for this critical exponent, which is 0.6, and actually consistent with those critical exponents that were obtained from Q equals to 0 DC susceptibility data. So that shows that there's really a connection between the criticality that is observed at finite wave vector and what's observed at Q equals to 0. And this is the expectation that we would have for a local quantum critical state. So to summarize, this material has no inversion, no point of inversion, and has no magnetic phase transition, and ends up in some kind of a local quantum critical state. And we could ask, is it possible that the biofermions that may exist in this compound are actually promoting this kind of critical phase? Because I will remind you that all of this is found in a stoichiometric compound, something which points towards the existence of an extended critical phase as opposed to really a critical point. So then let me summarize the whole talk and say that we were interested in the interplay between magnetism and charge transport in materials with protected Dirac and Weyl nodes. And we looked at a case of incommensurate magnetism promoted by, that we were able to show that it's promoted by Weyl fermions. We looked at the magnetic order in magnitude 3x And I explained that this is a magnetic antiferromagnetic order that has a character of ferromagnetism and therefore has all of the impacts on the quantum transport. But then I also described a very complicated spin charge modulated state in manganese 3 tin, where I think still much effort remains for us to really understand its origin. It totally extinguishes the anomalous Hall effect. And then finally, in serum ruthenium 410-6, we were led to thinking whether Weyl nodes could actually promote a quantum critical phase, which seems to exist in this material. So with that, thank you very much for your attention. I look forward to your questions.
Thanks, Collin. So it's time now for questions.
Collin, and thanks for the talk. I have a question about the first material.
Yes.
So I will reformulate what I understood, and you're going to say if it's right or wrong. So
All right.
my understanding is that, so you have your neodymium magnetic ions, which is local moments, then you have your metal around it. Your metal has some nesting in the Fermi surface, and therefore there will be a peak in the susceptibility of the metal at the corresponding wave vector. And this results in a RKKY interaction between neodymiums peaked at a certain wave vector.
Yes.
Okay, thank you.
So it's really a pretty, I think, it's a pretty, you could say that it's a fairly, standard situation. This is what we expect essentially for rare earth moments in the metal. But I think what is interesting in this case, I think we need to look at more of these kinds of compounds, is that these topologically protected band crossings, they have the tendency to lead to well-defined structures in momentum space. Because especially when they lie fairly close to the chemical potential, you get these little kind of pockets, or little, in the case of this material, there's fairly a large number of Weyl points. And so you get these kind of fairly localized structures that can lead to nesting. One of the things that I think is a little, that kind of acts in the opposite direction is that you end up having fairly low density of states at the chemical potential. They are, after all, semi-metals. But whatever, fermions you have available to mediate the exchange, they are of the Weyl character. So I think that there's, I think it's an interesting area to look at, and our goal with this compound was to make the connection, if you will, using DFT, etc., that we could really see that it was those Weyl fermions giving rise to the nesting.
Yeah, hello. I have a question concerning the cerium compound. You say you have this local quantum criticality type interpretation. You say that it's a critical phase. So is there a notion that alpha, your exponent alpha, changes somehow in this phase, or is it, how do you define this?
Yeah, I mean, it's a little, it's a kind of an inference, we would say, and we have to be frank about that. The idea is that there was nothing that was being tuned in this compound. This is a stoichiometric compound, and so then actually finding something which is critical at stoichiometry is either you're very lucky and you just landed specifically at the critical point, or there should be some kind of phase surrounding that condition, maybe as a function of doping or as a function of pressure, where the material would be expected to remain critical. But really, I would take that we should probably do more, work on this kind of compound to really explore and to show the presence of this critical phase. So for now, it's just saying that finding criticality in the stoichiometric compound we're taking it as an indication that this compound landed in some extended phase, because it would be too unlikely that it happened at a critical point.
Okay. Thank you.
Any more questions?
So it seems there are no further questions. Let's then thank Collin for such an excellent talk. And with this, we'll close this session. If there are any announcements, probably I'll leave it to